Learning at Google Distinguished Lecturer series. Joel Tropp, he's a professor in applied and computational math at CalTech, as many of you might know. He's made many contributions to signal processing, numerical analysis, random matrix theory, compressed sensing, and so on. I guess he's had many achievements, and I probably won't be able to say all of them, but I do want to mention two where he got the Presidential Early Career Award, which is very rare. And also, he was the most cited researcher in computer science, at least amongst the most cited ones, as defined by Thomas Reuters, right? In 2014 as well as 2015, two consecutive years. Great. And of course, he has many other accomplishments, including many best paper awards and other things that I wasn't going to, but take it away from there.
All right. Thanks, Hardy. I appreciate the invitation. It's a pleasure to be here. I last visited 10 years ago. Back when I was still working on sparse modeling. And so I'm happy to be back again on a campus that's unrecognizable, dynamic, and I'm happy to be telling you about something different. So a couple points of preamble. So first of all, I'm with the Department of Computing and Mathematical Sciences at CalTech, which consists of computer science, applied math, and control theory. So all of us are interested in computation and what you can accomplish with it. And so it's an exciting time for us too. And I think with that, I'm going to get started. I apologize if my voice is a little halting today. I'm feeling a little bit of dislocation from California. So, okay. I used to have the slide later in my talk, but I realized that perhaps it's best to start at the beginning. This talk is a pretty general interest, and I apologize if I'm telling you all things you already know. So I hope at least that I can entertain you slightly while doing that. And I will also remind you of a precept of Enrico Fermi, who said that one should never underestimate the pleasure one takes in hearing something one already knows. Okay, so what is a random matrix? So some people would say that it's a measurable function taking matrix values, but let's forget about all that. It's just a grid whose entries are random numbers that aren't necessarily independent of each other. Okay, so I have here in captivity a random matrix that I found in the wild. And there are a few things I want you to notice about this. So some of the entries aren't actually random. So you can see that the diagonal and the counter diagonal are both 0. So there's some structure here. Furthermore, the off-diagonal entries are the same. So it's got a sort of turplet structure in addition to the 0 pattern in the matrix. But modulo those constraints, the other entries really are random. Insofar as MATLAB will have you believe that it generates random numbers. And so one of the things I'd like to emphasize by starting with this example is that the kind of random matrices you come across in contemporary applications, for example, machine learning, are pretty complicated, and they have a lot of structure in them, even though they also contain random numbers. And somehow, you'd like to be able to understand these random matrices, even though they have more complicated structural properties than the kind of random matrices that were studied historically in some areas that I'll tell you about in a few minutes. So that's the big challenge, understanding modern random matrices where the entries aren't all independent from each other. So this is a random matrix, and the question that you might ask is what we want to understand about these random matrices. Why is this an object of inquiry? Why is it a different subject even from probability? So the reason is because random matrices are linear maps. They're models for linear maps. So that means that you can multiply things into the random matrix, and other things come out the other side, which at that point are also random. And understanding the action of a random matrix is what makes random matrices more challenging and more interesting than ordinary random variables, which are just numbers. You don't necessarily think about them as having a functional action. And so when you take this perspective, you immediately see that the kinds of things that we're going to be interested in are spectral properties of the matrix, like the eigenvalues and eigenvectors if it's square or symmetric. In which case, these are vectors that, when you multiply them into the random matrix, are preserved up to their scale. So it's connected with the action of the matrix. The eigenvalues are the scale factors on these vectors that are preserved under the action of the matrix. It tells you how much the random matrix can inflate vectors or compress them. The singular values and singular vectors are relevant both for square matrices and for more general matrices. And they also are connected with how much the random matrix can dilate or compress vectors. So these are the most important properties. You might also be interested in operator norms, which also depend more in a more complicated way on the geometry of the domain and the codomain of the random matrix, but I'm not going to be talking about that today. Now, when you look up random matrix theory on Wikipedia or on Google Scholar, you'll find that there are an enormous number of papers on this subject, and it has very classical roots that I'll describe to you in just a moment. And there are a lot of books in which you can go read about random matrices as they arise, in particular in statistics, here in Muirhead, in mathematical physics, here in Mehta, in operator algebras, here in Nika and Speicher, and again in statistics in Bai and Silverstein. So there are a lot of places these things have come up. Oh, and Terry Tao also has a nice book on this, which is a little bit more contemporary in its outlook. So all of these are distinguished by their focus on what I would call classical random matrix ensembles, which are random matrix ensembles that consists of random matrices whose entries mostly are independent from each other, where the random matrix has an enormous number of symmetries. For example, the distribution is invariant under rotations. And that makes for a very beautiful theory, but it also makes it somewhat inapplicable to problems in contemporary machine learning or in contemporary numerical analysis, which are the areas that I'm most interested in. And so the challenge is to understand these properties of random matrices for the kind of random matrices that come up in our lives as researchers. Okay, so let's take a look back at some of the places that random matrices have arisen, and I'm going to emphasize a little bit about how the examples that people looked at before are not as complicated as the ones that we look at now. So Peter Forrester told me that in his view, random matrix theory dates to work of Hurwitz in the 1890s on integration of functions over groups. Okay, so there's a very deep geometric interpretation. The idea being that if you take a generic element from the orthogonal group, it's represented by a matrix, and that is a random matrix if you draw this uniformly. But I think that if you try and see where random matrices first made contact with applications, the first paper that I'm aware of is a work by John Wishart in 1928 from Biometrica. So Wishart was a student of R.A. Fisher, and he was interested in models for populations where you measured multiple variables for each member of the population. And because this is statistics, you think about drawing a random sample from the population. And so you have independent observations of a number of variables for each of a number of subjects. And you can form the sample covariance for this ensemble, and then you can try and ask what that sample covariance matrix looks like. Now, back in the 20s, a computer was a person and not a machine, and so statisticians tended to focus on analytical methods rather than computational methods. And so Wishart studied the case where the random variables attached to each subject followed a multivariate normal distribution. And he wanted to understand what the sample covariance matrix looks like for a multivariate normal population. And he worked that out, and you have here a very complicated formula for the joint distributions of the eigenvalues of a what's called a Wishart matrix now, the sample covariance of a normal population. And I personally don't find this enormously enlightening, but the advantage of things like this is that you can perform analysis on them, you can tabulate them, and thereby start to do statistics under normal population assumptions. And the thing I want to emphasize about this work is that Wishart was studying a very special kind of random matrix. The entries are derived directly from Gaussian random variables with multivariate Gaussian distribution. And if you don't have sophisticated computational tools at your disposal, this may be a reasonable assumption, but it also leads to a very specialized theory, which has endured and is still taught in some statistics departments now. Okay, now the next place, which is less familiar, in which random matrices arose, is in numerical linear algebra. So this smiling gentleman here is John von Neumann, standing next to his first digital computer. Turns out the first digital computer was actually built in Germany by Konrad Zuse. But von Neumann had one of the first digital computers, and he was interested in what you could do with this. And being involved with the military, he was interested in, among other things, studying dynamical systems and solving problems involving ordinary differential equations. And one of the challenges that he was interested in was even more basic, and that was the problem of solving linear systems. So how do you solve a linear system on a computer? Now, before von Neumann ever had a computer, say 3 or 4 years before this photo was taken, he wrote a remarkable paper which appeared in the Bulletin of the AMS in 1947. This computer didn't arrive until the early 50s, in which he developed the LU algorithm, or the LU decomposition of a matrix, algorithms for computing the LU decomposition, an error analysis for the LU decomposition, and really established the foundations of the entire field of numerical linear algebra. So it's really a remarkable achievement since he couldn't actually implement any of this at the time. But he really foresaw that there is a prospect for using computers to solve large-scale linear systems, large probably being like 30 or 40 or something back then. Okay, I don't actually know that. Okay, so what does that have to do with random matrices? So if any of you studied numerical linear algebra, say 15 years ago, you would have learned that numerical analysts hate randomness. And so it was interesting that even in the second paper that von Neumann wrote about this, there was actually a random matrix. So what was he using it for? He understood that when you make this computation of the LU decomposition, that you make mistakes because you can't store the numbers to arbitrary precision. And so every time you round, you induce an error. And so he was trying to understand what typical errors might look like, and he figured, well, maybe they're random. And so he posed a random model for the matrix of errors you obtain in performing an LU decomposition. And he was interested in how big those errors might be in the spectral norm, and he obtained a formula here, an upper bound. Now, This result is actually one of the earliest results on random matrix theory. He had to derive this more or less from scratch at the time. The one thing I'll emphasize is that this, again, is for a matrix with independent Gaussian entries, which is perhaps an okay model in this setting, if you believe floating point errors are Gaussian. But nevertheless, it's still a very specialized example. Okay, so random matrices turned up in numerical linear algebra, and then they vanished again until about 10, 15 years ago, where they emerged with full force and are now a major tool for solving linear algebra problems in practice. And that's one of the interesting applications of the work I'm going to be telling you about today. Now we finally come to the example that people are probably most familiar with or have heard about the most. So this smiling gentleman is Eugene Wigner, after he has won the Nobel Prize. And Wigner was a nuclear physicist, and he was interested in modeling slow nuclear reactions involving heavy atoms. Now, so if you take like quantum mechanics or something, they really talk to you about the theory of the hydrogen atom, and you can work everything out in great detail. But when you're talking about an atom that has hundreds of protons and neutrons, things are a little bit more complicated, and you can't do this by hand. And so Wigner had the idea that you could think about the Hamiltonian describing a reaction involving one of these atoms as being a random object, subject only to the symmetries that you knew must be present in that system. And so he posed the idea that you could use random matrices to understand nuclear physics, which turns out to be a fruitful idea with some asterisks from the point of view of nuclear physics. But more to the point, he wrote a famous paper in Annals of Mathematics in 1955 in which he studied what we now call a Wigner matrix, which is a symmetric matrix whose entries above the diagonal are independent from each other and have the same distribution. In this case, they're Rademachers. They're equally likely to be plus or minus one random variables. And here's an excerpt from his paper in which he starts to derive the limiting spectral distribution of this random matrix, what the eigenvalues of such a matrix look like when the matrix is large. And so this was really when random matrix theory started to catch the attention of mathematicians and started to develop into a subject of its own right. But again, I want to emphasize that a Wigner matrix is a very special thing. The entries are all independent, they all have the same distribution, and the only constraint on the matrix is that it's symmetric. So a very special model. It's led to a lot of very fruitful mathematics, but it doesn't have much to do with the kind of problems that we're trying to solve now. Okay, now what kind of problems are we trying to solve? So here is a list of areas in which random matrix theory now plays a role. So I'm not going to read these out. I'll call out machine learning since this is a machine learning seminar. But there are a huge number of fields in which random matrices are now making a really fundamental impact. The ones that I like best are actually in optimization, numerical linear algebra, and numerical analysis, for the reason that in these applications, you are often designing algorithms that harness the properties of random matrices to ensure that the algorithms are correct and effective. So the random matrix is an engineering design choice for an algorithm, and because that is a design choice, you can be very confident that the algorithm is doing what you expect that it does. And so the random matrix really belongs there. You've built into the algorithm, your analysis relies on the properties of random matrices, and therefore you can be confident that your algorithm is correct. And many of these other places, people use random matrices as a modeling tool, and these are only useful to the extent that the models are valid. And so it's a small distinction that I like to make, and it's something to keep in mind when you're doing high-dimensional statistics. You can write down random matrix models, but you do need to interrogate whether they describe the data that you're interested in. One place where they do, by the way, is in wireless communication. So people use random matrices to describe wireless channels, and this is considered to be a rather good model. Okay, so since 2000, according to Google Scholar, there are at least 23,400 papers on random matrix theory, and I have chosen some randomly, non-uniformly. I mean, on the other hand, probably if you look on Google about the number of cat photos that have been posted since yesterday, that exceeds 23,400. So one might argue that photos of cats are more important than random matrices, but I'm not a cat scholar, so this is what we're talking about today. So what I'd like to discuss is an approach to dealing with the random matrices that show up in the problems that I was describing, and in particular, the kind of random matrices that people use to study numerical algorithms, where you often have goals of using random matrices that are built out of things like discrete Fourier transforms or out of random sampling that are not subject to the laws of Wigner or Wishart. Okay. Any questions on the backstory before we move on into the more technical part of the presentation? All right, forthwith. So the method I'm going to be talking about is called matrix concentration. And I want to motivate this first by talking about scalar concentration, which is something that's familiar to a lot of people now. So I'm going to be fairly brief about this. But I like to use this as a model for the matrix results. So what is concentration? So many of you have probably seen Chernoff bounds in some form or another. And these are one of the prototypical examples of of scalar concentration inequalities. But concentration is actually a broader phenomenon that occurs in probability. And the key idea is encapsulated in this quote by Michel Talleyrand, who said that a random variable that depends nicely on a lot of independent constituents but is not controlled so much by any particular example, this random variable is more or less a constant. It doesn't really fluctuate very much. And so you can try to quantify that using a probability inequality like this one, the very rigorous statement here that if a scalar random variable z is, the probability the scalar random variable z is close to its mean, its expected value, the probability that that's large is negligible, provided that large is, this parameter t is not too small. So the goal in studying concentration is to understand how big t needs to be before this kind of statement is true, and also how the right-hand side depends on this parameter t. How fast does it decay? All right. So scalar concentration says that random variables are often close to their mean value. That's their typical conformation. So what's an example of a random variable that concentrates? So the paradigmatic example is the simple random walk. So the random variable z we're going to talk about here is made up of 10,000 independent random variables. Each one of these independent random variables is a step, either to the right or to the left, chosen at random with equal probability. So the sum z is the location of this random walker, who at each step decides arbitrarily whether to move left or right. Z is the location of this random walker after 10,000 steps. Now, it's clear if you think about it for a moment that if your walker were very concerted, he might have made 10,000 steps in the positive direction. Or he might have made 10,000 steps in the negative direction, and after 10,000 steps arrived all the way out here at 10,000. Now, we don't really think that's very likely to happen because every time he takes a step, he's flipping a coin to decide whether to go left or whether to go right. And what actually happens is striking. It's clear that the expectation of this random variable is 0 because expectation is linear and each of these increments has mean 0. So on average, you expect to be at 0. But typically, where are you after 10,000 steps? What's striking is that you are typically only about 100 steps away from where you started, in spite of the fact that you could have taken 10,000 steps. Now, the number 100 is relevant here because it's the standard deviation of the random variable z. So it's unlikely that this random variable, the final location, is more than a couple standard deviations away from the mean. And as you probably know, this is well described by the central limit theorem, which will give pretty accurate probability estimates for this. But the key point here is that even though you could have taken 10,000 steps in either direction, you are actually in a much, much smaller range. So in other words, z concentrates around its mean value 0. The typical realization of this random walk winds up close to where it started. The usual precept here is that the best place to find a drunk is outside of the bar. Okay, so any questions on this example? Okay, you've probably all seen this. Now, one way to quantify the probabilities, which is not as sharp as the central limit theorem, but has the advantage of applying in the finite setting and to be very simple to use, is called Bernstein's inequality. So Bernstein's inequality is a bit more general, although it also applies in particular to the random walk example. So S1, S2, S3, and so forth are independent random variables taking real values. So these are just random numbers. And I'm going to assume that each one is mean 0 just to keep all the formulas simple. And we're also going to assume that none of these random variables can be very large. So it's not like at some point you could take a step of 500 feet. Every time you take a step, it's 1 foot left or 1 foot right. Okay? So this is Talleyrand's precept that no one random variable should contribute very much to the sum. Okay, then Bernstein's inequality states that the probability that the sum of these independent random variables is bigger than t is not so big. So it decays quadratic, so it's exponentially small. The exponent decays quadratically in t when t is not so big on a scale of the variance of the random variable. So what this is saying is that it's likely to be Gaussian, close to 0 in behavior. So the scale of medium deviations is the standard deviation. But for large fluctuations, something different happens. You can see that these two t's here cancel. And so for very large deviations, the tail is more like an exponential on the scale of L, the bound. So there are only two ways that a sum of independent random variables can be big. One of which is that there's a lot of fluctuation in total. That's when the variance is big. The other possibility is that a modest number of the summands themselves are actually large. Those are the only two possibilities, and Bernstein's inequality captures that. So here's a schematic that shows you what this looks like. Note that the probabilities here are on a logarithmic scale. So Bernstein's inequality tells you that at first, the probabilities drop off, the log probabilities drop off quadratically on a scale of the standard deviation, the square root of the variance, and then eventually, somewhere along the line, it flattens out and the log probability starts to decay linearly on a scale of 1 over L. All right, so this is what Bernstein's inequality tells you. And what you can see here is that the probability of being 2 standard deviations away from the mean is only 27% already at most. It's actually smaller than that for the random walk example. And at most 3 standard deviations with probability only 2.2%. And the advantage of Bernstein's inequality applies to any kind of independent sum of random variables, no matter what their distribution is. This is a very powerful thing. It's totally distribution independent, and it gives you good predictions, good bounds for this probability. So it's a very useful tool. So let me ask if there are any questions about Bernstein's inequality before I continue. Okay, great. So there are lots and lots of concentration inequalities for scalar random variables. This is a very active subject that dates back at least to the 20s in some form or another. People often call these things Chernoff bounds. You'll notice that Chernoff is not the first name in this list. Chernoff was working in the 50s. These ideas date at least back to Bernstein's work in the 20s. And really, you can even trace this back to work of Markov and Chebyshev in the late 19th century. So it's a very active subject. These results all have different collections of hypotheses and conclusions, and altogether they form an invaluable toolbox for anyone working with probability. And by the time you get to the bottom of this list, we've moved well beyond independent sums of random variables to much more complicated kinds of objects. So by the time you're at the bottom, you've got results that apply to functions of independent random variables. And the function can be somewhat general. The quality of the result depends a lot on the function. But nevertheless, any function of independent random variables that depends weakly on each of the random variables and is smooth will concentrate around its typical value. It's a very powerful precept, and this whole line of work has been dedicated to elaborating on this idea. Great. So now I want to talk about matrix concentration. So random matrices are, I hope I've been able to demonstrate, a very important type of random object that we encounter a lot. But they're not as easy to study, and they don't have the same kind of detailed history that these scalar results do, even though random matrix theory is a pretty old field. And part of the problem is that the models people were using were not very general. And so I want to talk about a class of results called matrix concentration results that extend these scalar ideas to matrices, but apply to a whole lot of examples. So the way that I like to think about matrix concentration is using the following adaptation of Talleyrand's principle. So a random matrix depends in a smooth way on the influence of a lot of independent random variables, or, for example, a lot of independent random matrices, but doesn't depend too much on any one of them, is pretty close to a constant matrix. Now, the way we're going to quantify this is a little bit different from the way we quantified this in the scalar setting. You could think about trying to study the entries of the random matrix, or you could think about trying to study the total energy of the random matrix, but those quantities don't have anything to do with the way the matrix acts on vectors. So instead, we're going to look at the spectral norm, which is the maximum singular value, also known as the L2 operator norm. We're going to use that to quantify when two matrices are close together. I'm going to explain in a moment why this is such a useful way of controlling the discrepancy. And so the claim here is that if Z is a matrix-valued random variable, and you take the expectation of each entry of the matrix, you get another matrix. And what I'm asserting here is that the spectral norm distance between Z and its mean is typically not too big. And the challenge, again, is to understand how big T needs to be for the right-hand side to be small, and also how the right-hand side here depends on the parameter T and the properties of the random matrix Z. So that's the goal of matrix concentration, to produce results of this form. Okay? And the differences between what I showed you before and this slide are that Z is now a random matrix instead of a random scalar. And instead of using the absolute value to measure discrepancy, I'm using the spectral norm. If Z were a 1-by-1 random matrix, which is also known as a random scalar, this would collapse to the formula on the previous slide. Great. So here's an example of a random matrix that can be written as a sum of random matrices. This is a sample covariance matrix, the kind of object that Wishart studied back in 1928, except that now we're not going to focus on the normal distribution. We're going to allow the random variables associated with each member of the sample to have an arbitrary distribution, subject to some mild constraints. So here's how we frame this. Let X be a p-dimensional random vector. So this is statistics land. P is the number of variables. And we're going to assume that this random vector of length p has mean 0. This is all for simplicity. You can also consider non-centered examples. So the covariance matrix of this random vector is the matrix A that you obtain by taking the expectation of XX transpose. I'm going to use the star here for transpose or conjugate transpose. And this is the matrix that we obtain by tabulating all of the covariances between the individual entries of X. So it's a P by P matrix. It is deterministic, not random. Okay? And the reason this is a covariance is because I assumed everything is mean 0, so we don't have to do any centering. Now, the sample covariance is a method for estimating the covariance from data. So suppose that we have drawn independent copies of this random vector. So we looked in this population, and we pulled out a subject and measured p variables for this subject. We pulled out another subject from the population. We measured her p variables. And then we continued this process until we'd collected data for n subjects. And we'd like to understand the covariance of the family of random variables from the observed data. So we can do that by taking the observed samples and forming what's called a plug-in estimator. So instead of taking the average over the actual distribution, we're going to replace the mean by an empirical average of the stuff we observed. Now, this is a random matrix because the xi's are random, and we think that if we take a lot of data, this thing's going to converge to the population covariance because of the law of large numbers. Each entry will eventually converge. So that's true, but the question is how many samples we need before this happens and how well this estimate for the sample covariance, the sample covariance matches the population covariance. It's not hard to see that it's an unbiased estimator because the expectation passes through here and we just get the average of n copies of the population covariance. And so it's natural for us to ask how well an hat, the sample covariance using n pieces of data, approximates the population covariance and spectral norm. And we'd like to know how many samples n we need to make this small. So a very basic question in modern statistics. The difference between this and what Wishart did is that now the distribution ain't normal. It's arbitrary at this point. Okay, now, how are we going to deal with this? So I want you to notice that the sample covariance matrix is a sum of independent random matrices. And it turns out that this type of model is tremendously common in a wide range of applications. And so we're going to abstract this out. So we're going to consider random matrices Z that are obtained by adding up independent random matrices Sk. And the sample covariance is one example, but there are dozens of others, which is why these tools have been so useful in so many disciplines. So the scalar concentration inequalities don't apply to a random matrix like Z directly, unless you were to look at, say, the entries. What people would typically do, actually, is look at the spectral norm of the random matrix, and scalar concentration results may tell us that the spectral norm of the random matrix concentrates around the mean spectral norm. Okay? So this one number, the size of the random matrix, is close to its typical size. The matrix concentration results, in contrast, tell us that Z as a random matrix is close to the expectation of Z as a deterministic matrix in spectral norm. So these formulas look similar to each other, but this one happens to be more powerful for a lot of purposes because this one doesn't tell us anything about how big the expected norm of Z is. It's just something you would have to know. Here, this is something that is actually not very hard to compute. It's pretty straightforward in many settings to compute the expectation of Z as a matrix. And understanding how far Z is from its mean tells us a lot of other things. It tells us that the singular values of Z and its mean are close to each other. It tells us the singular value vectors are close for isolated singular values. Tells us that all linear functionals of z are close to the corresponding linear functionals of the expectation of z. And furthermore, this is actually probably the most important point, we obtain a bound for the expected spectral norm of z, the quantity we didn't have here, just by using the triangle inequality. We add and subtract the norm, the expectation of z, and we see that the expectation of the norm of z is close to the norm of the expectation of z, which we can often compute, plus a fluctuation term, how far z is likely to be from its mean. And so using matrix concentration, we can get estimates for this quantity. It's usually not very hard to estimate the expectation as a matrix, and therefore this theory as a consequence gives us the typical size of a random matrix, which is actually quite hard to get your hands on. And that's what makes these results hard to use. So together, these results allow you to understand how big the random matrix is typically, and then you can understand, how big the random matrix is on average, and then you can understand how big it is typically using scalar concentration. Okay, let me pause and ask if there are any questions on that. It's after lunch. It's a lot easier to talk for an hour than it is to listen for an hour, I understand. So, okay, good. So matrix concentration is telling us something fundamentally different from scalar concentration. And the simplest tools, the ones I'm going to tell you about, apply to sums of independent random matrices. So we have a theorem that I call the matrix Bernstein inequality that applies in exactly this setting. So we have a family of independent random matrices that are D1 by D2. We're going to assume each one is mean 0, and we're going to assume that each one is bounded in spectral norm. So none of the summands are too big. Each one is centered around 0. Again, this is just to keep things simple. Now, the claim of this theorem is that for large T, the probability that the sum is large is controlled by this expression. So you can see that there's a dimensional parameter here that we obtain by adding up the two dimensions. That's new. But the rest of the expression looks similar to before. It depends quadratically on t for small t on a scale of v, which is a notion of variance that I'll talk about in a second. And for large t, this t squared and this t cancel to give us a t, so we get an exponential behavior on the scale of L, which is the bound for sk, just like in the Bernstein inequality. So the two differences between this and the Bernstein inequality are that we're using spectral norms now instead of absolute values. We have this dimensional factor, and now the variance has a new definition. So first, let's talk about the dimension. So suppose that D1 and D2 were both 1. These random matrices then would be scalars, in which case D here is 2, and we recover the scalar Bernstein inequality. So the scalar Bernstein inequality is a corollary of this result. It tells us we haven't lost anything in that setting. Now, on the other hand, if D is bigger, then we pay for it, and I'll show you how in a minute. The second point is that the notion of variance has changed here. So remember in the scalar case, the variance was the sum of the expected squares of the summands. Now, can you square a rectangular matrix? No. You cannot square a rectangular matrix. In fact, it has two squares that are different from each other. One is XX transpose. The other is X transpose X. Those are both square matrices, which you can reasonably interpret as squares of X. They're different from each other, and in general, they actually don't have anything to do with each other. Okay? And so to compute the variance in the matrix setting, we have to look at both squares, the one we obtained by taking SK transpose, taking the expectation, and then taking the norm. And we also have to do the same thing with the transpose in the other place. And then we have to take the bigger of those two numbers. And this is essential. You can't get away with one or the other. You need both of them. But in particular, if these were numbers, both this and this are the same, this whole thing collapses to the variance we defined in the scalar Bernstein inequality. And so again, there's no loss here in this setting. Now, what's mysterious about this as compared with the scalar setting is this dimensional parameter. And so it's a little bit easier to understand how the dimensional parameter plays a role if we pass from the result that I just showed you to an expectation bound. As I said before, the real importance of these things is actually getting bounds on the average size of the random matrix, the expected spectral norm. That's even more useful than the tail probabilities because you can get those out of scalar concentration. So the result can also be interpreted as saying is that the expected norm of a sum of independent random matrices is controlled by the square root of the variance times the log of the dimensional parameter plus the maximum size of any of the terms times the log of the dimensional parameter. So we pay very weakly for the size of the random matrices here. And it turns out that's inevitable, as I'll explain in a moment. So the point here is that we have these extra log factors that pop out in the matrix setting that weren't there before. But the only two ways that a sum of independent random matrices can be big is if the total fluctuation is big or a modest number of the terms individually happen to be large. Those are the only two possibilities, and that's what this result tells us, just like in the scalar setting. Okay. Questions on the statement of this result? Yeah?
So you don't have any assumption about the entries of each of
Nope.
the matrices?
No, they can be arbitrarily correlated.
That could come up in the V somehow? Or?
Yeah, you've got to compute the expected squares, and the more complicated the matrices are, the harder that might be. But that's actually a good point. Computing V is usually a little bit of probability and a little bit of linear algebra. It's actually not that hard. That's part of the reason that these results are powerful, is that you have to be a little bit careful, but it really reduces these random matrix problems to arithmetic. The arithmetic might be a little tricky, but it's arithmetic nonetheless. Okay. Anything else? Yeah, Artie.
So here S has to be the sample covariance matrix? It doesn't
No, it's arbitrary. It's arbitrary.
So for that
In particular, it applies to the sample covariance.
there is
Next
a
slide.
ortho
Yeah. Yeah. For sample covariances, there are easier things you can do, in fact. You use Chernoff bounds. That's easy. Okay, good. So the main difference schematically between the matrix Bernstein and the scalar Bernstein inequality is that the matrix Bernstein inequality doesn't operate for small t. It doesn't give you any information. You have to be all the way out here at this number before the inequality starts to give you non-trivial probability bounds. But then it decays quadratically on a scale of the standard deviation, and then it starts to decay linearly on a scale of L farther out. Okay? So that's the main difference. This whole curve is shifted over to the right by this amount. Okay, good. So what does this have to do with sample covariance matrices? So we're back in the same setting as before. I'm now going to insist that each of these random vectors is bounded in L2 norm. So it has finite energy. This can be relaxed if you do things differently. And again, we take independent copies of X. The population covariance is the matrix A given by the expectation of X times its transpose. And here's the sample covariance estimator. And our goal is to understand how far away the sample covariance is from the population covariance using the matrix Bernstein inequality. And we don't actually have to do anything. We just plug in the parameters, and we obtain 2b times the norm of the population covariance times the log of twice the number of variables divided by the number of samples, plus another term that depends on the size of each of the summands, the log of the number of variables, and is inversely proportional to the number of samples. Okay, so you can see how this form looks a lot like the outcome of the matrix Bernstein inequality. It's just a little bit of arithmetic to get this from the assumptions. Now, what does this mean, practically speaking? So suppose that the number of samples is proportional to the bound on the size of the random vectors. proportional to the logarithm of the number of variables, so it depends weakly on the number of variables, is inversely proportional to epsilon squared, and is inversely proportional to the norm of the population covariance. Then we achieve relative error in estimating the sample covariance matrix on order epsilon. Now, this formula is still not that enlightening, so what are the typical parameter values? Think about the norm of A being 1, like the population covariance is the identity. So the variables are uncorrelated with each other. In that case, you're typically going to have the upper bound parameter on the order of the number of total parameters, p. And in this case, this bound for the sample complexity simplifies to p log p. So the number of samples you need is proportional to the number of variables times the log of the number of variables divided by the square of the accuracy that you want. So this is optimal. So for worst case distributions, you need both the p and the log p. And furthermore, if you want very accurate estimates, the central limit theorem tells you you're not going to beat that epsilon squared. Okay. So this matrix Bernstein inequality makes short work of what was actually considered to be a major open question in statistics until the work of Rudelson in the late 90s. And these ideas, in some sense, are just a refinement and packaging of some of the work that he did then. So this is the application to sample covariance matrices. Let me pause and ask if there are any questions on that. Okay. So what I want to emphasize here is that this is a problem of basic importance in statistics. We've expressed the sample covariance as an independent sum. We have made a trivial application of the matrix Bernstein inequality, and we have obtained a result that is optimal for the general case. Whereas this is something that required in the past the attention of Fields Medal winners, and now you can do it at home. Okay. Now, you might wonder whether this bound is optimal or not. This is different from the commercials. You should try this at home. It turns out that this result is optimal. So there's a matching lower bound, which says that in this setting, the expected norm of a sum of independent random matrices is also bounded below by the square root of the variance plus the upper bound. The difference between the left-hand side and the right-hand side is the logarithm of the ambient dimension, and one might wonder if we can get rid of that. So if you're, say, a theoretical computer scientist, you'll say, what are a few logarithms between friends? And you will call it a day. Not everyone is that cavalier, and some people are actually very concerned about the presence of this logarithm. Unfortunately, it turns out that without extra information, you can't decide whether the bound on this is closer to this quantity or whether it's closer to this quantity. So there are examples where the lower bound is pretty accurate, like a Wigner matrix. And there are also examples where the upper bound describes the behavior correctly. So a Toeplitz matrix with random entries in the first row and column sits up here. Okay? So it's an exercise to see how you can apply these tools to Toeplitz matrices. And so the point is that without extra information, the matrix Bernstein inequality is as good as it gets. But even so, at worst, you've lost a logarithmic factor in the dimension. So not too bad. And there's a major open question here, which is whether there's a simple way to decide whether this bound is more accurate or whether the answer should be closer to this. I wasted roughly 2 years on this question, and I'm trying to put this in the rearview mirror. So I'll say one word about the proof before we wrap up. So this is based on an idea called the matrix Laplace transform method, which turns out to be a very direct extension of the scalar Laplace transform method, which we prove Bernstein's inequality with in the classical literature. So the idea here is you've got the probability this independent sum is large, and you use Markov's, you multiply both sides by theta, you exponentiate, then you apply Markov's inequality to get here. So this is just Markov's inequality. Then you notice that the exponential of a sum is the product of exponentials. The expectation of a product of independent variables is the product of the expectations. The log of a product is a sum, and therefore this quantity here, this cumulant generating function of this independent sum, is the sum of the cumulant generating functions. All right, and then after that you just have to pick the right theta and you're done. Now, in the matrix case, it turns out a similar proof works, except that it's not element.
That took you 2 years to figure out?
Oh, worse. That took me decades. I'm a slow worker, so, you know. No, so this is actually Bernstein's idea. We go back to the 20s, in spite of the fact that it's attributed to Chernoff. Chernoff apparently attributed it to Charles Stein, by the way. So go figure. All right, it turns out that in the matrix setting, there is a similar proof which turns out to be highly non-trivial. So the first step is to look at the maximum eigenvalue of the sum. So these are Hermitian now instead of rectangular. You look at the maximum eigenvalue of the sum, you multiply by theta, you exponentiate, you apply Markov's inequality, you pull the maximum eigenvalue out of the exponential, and then you bound that by the trace. So that's trivial, almost, and you get here. And so now you have a matrix cumulant generating function. Unfortunately, it is not true that the matrix cumulant generating function of an independent sum is the sum of the cumulant generating functions. But something even better is true. It turns out that it's bounded above by the sum of the cumulant generating functions in some sense. And so you actually get an inequality here. This is a deep result due to Elliott Lieb from 1973, which is one of the crown jewels of matrix analysis. So the difference between this and this is very little in terms of edit distance on my slide, but is very large in terms of conceptual distance. Okay, good. So there are zillions of other matrix concentration inequalities, and the ones here at the bottom apply to random matrices that are given as functions of independent random variables. And we haven't found a lot of applications for these things yet, but I'm optimistic that you smart people who take this home and try it will find applications. There are a few, including things like multi-class learning and compound sample covariance matrices and things. But right now, the more sophisticated results like matrix McDiarmid and Efron-Stein are underutilized. Great. In summary, I view this whole line of work as a collection of simple but extremely powerful tools for applied random matrix theory, and they help you make short work of structured random matrices that turn up in the applications that you care about, and they allow you to do things that you used to have to be a Fields medalist to do. And what's been really gratifying about this line of research to me is that I think that people have found these tools really empowering. They've been able to go out and do all sorts of exciting, creative things that wouldn't have been possible if they had to spend all their time worrying about what random matrices look like. And I hope now that these methods will enable even more research like this to occur. Thank you for your attention. And here's a list of papers on this subject. I got a little obsessed. And with that, I close. Yeah, please.
So that gap before the matrix Bernstein kicks in, is that sharp? Are there like these really anti-concentrated matrices that just don't do anything until then?
Oh, you mean here on the in this picture? Yeah.
Is that like just if I take normals, IID normals?
No, normals you do a bit better. So what's more relevant is this gap here. Are there logarithms or are there not logarithms? That is the question. For it's not even a matter of whether it's normal or not normal. It has more to do with the structure. So roughly speaking, if the summands commute with each other or almost commute with each other, you're going to pay for the logarithm. On the other hand, if the summands have nothing to do with each other, they have a lot of cancellation with each other, you don't expect to pay for the logarithm. But it's very hard to quantify this intuition. That's what took me 2 years to discover. And so understanding which of these bounds is closer to being correct, the lower bound or the upper bound, is a huge problem.
Because I know if I want to take like, if I want to get like optimally anti-concentrated scalars, I'll take Gaussians. But so what would be like a optimally anti-concentrated structure?
Turplets. So the reason is that you can think about so I'll answer the homework problem. You can write a Toeplitz matrix as a sum of independent random diagonal matrices. So each of the off diagonals gets its own summand. And so the problem is that these are all roughly shift matrices multiplied, powers of shift matrices multiplied by random scalars, and the shift matrices basically commute with each other. Not quite, but powers of shift matrices almost commute. And so what happens is that in some sense it's really more like a scalar problem than a matrix problem. And so the logarithm comes from somehow the maximum of a collection of d independent random variables being something like the square root of the logarithm of the variance of the biggest variable. Okay, maybe TMI. More questions?
Is there a tensor version of this talk? Or?
If you believe that tensors are simply Kronecker products and that you should use the ordinary operator norm as the Kronecker product, absolutely. But if you mean like maximum eigenvalues of tensors, no. I mean, all this depends heavily on the convexity properties of bilinear objects. So it all breaks as soon as you make things multilinear, or multi means 3 or more. Yeah. Yeah. Please.
So I think you had a slide on my question, which didn't quite sink in for me.
Mm-hmm.
So my question is, you're looking at the spectral norm of a random matrix, which depends on a bunch of random variables. It is also just a function depending on a bunch of random variables. So how would you compare these to, for example, Efron-Stein and some of the later results on functions, general functions?
Yeah, so in particular, the sum is a function of independent random variables. It's known in the scalar setting that somehow independent sums are the least concentrated of all functions of independent random variables, and that's what Efron-Stein tells you. So it turns out that in the matrix case, there are versions of Efron-Stein as well that apply to more interesting functions of independent randomness than just sums. The results are complicated, though, and they're maybe not so easy to use, but they exist. I'm just not sure I've answered your question yet.
I guess I'm just wondering, the spectral norm of z minus expectation of z, it's a function, scalar valued function.
The matrix valued function, right? I mean, each of the entries is a scalar, but what?
So once you take the norm,
Yeah, the norm is a scalar valued function.
so I wonder how do you compare with just straight?
So, it's this point here. So in scalar concentration, you get information about how the norm of the random matrix concentrates around the mean, the expected norm. The problem is that it's very, very hard to get estimates for the expected norm of a random matrix. This is a major question in probability theory. And so even though you might know that the norm concentrates around its typical value, you don't know what the typical value is. And one of the incredible things about these matrix concentration tools is that they actually give you ways to estimate the expected norm. And so that's, in my view, the main value of these techniques. They tell you how big the random matrix is on average, and then if you wanted to study it using scalar methods, you want to study the norm using scalar methods, you have this extra piece of information, you can do that.
guess the question is the second thing, right? The norm
Yeah.
of z minus expectation of
Yep.
z. It's also a scalar, right?
It is.
It's just a norm, and it depends smoothly and
Yep.
nicely on
Yep.
some random variable. So what if you just apply the scalar results, like the more advanced ones?
You can't, because the norm of this is some number, some random number. You'd have to compute its mean to be able to apply the scalar results to it. That's the problem. And so you need this quantity here. You don't have that quantity. Matrix concentration gives you that quantity. That makes sense? Yeah. It's kind of a subtle distinction. More questions?
It's time to.
Great, thank you.